All right, everyone. So this is sort of our last lecture in our main lecture series. So we've talked a lot about how semiconductors work, how photoelectrochemical systems work, how all these interfaces allow charges to go back and forth, how we can generate voltages and current, how we can get power out of these devices. We looked at recombination and some of these things that can affect the semiconductor's efficiency. And today we want to look at some work that's actually being done in the field, something that wasn't discovered like 60 years ago. So the first paper that we're looking into is what's called an accounts chem research, or account of chemical research. It's a journal that just it's where like a professor will publish sort of a summary paper on the work that they've done so far. And so it's not a strictly research paper, but it's based on a couple of research papers. And it's by the Boettcher Group over at Oregon. Shannon Boettcher is a Lewis Group alum. He was a postdoc with Nate some years back. So what he's looking at is a system kind of like this. So what we have is our N-type semiconductor. We have a catalyst in here and a redox couple. So this is similar to what we've been seeing before in that we have a whole bunch of interfaces. We just sort of added a third thing. We've added this catalyst. Now the catalyst gets a little bit complicated. For example, you might notice that in fact this catalyst level down here doesn't quite match up with the redox potential. And the reason it doesn't is because there's this thing called overpotential. And so in order for this thing to actually, this is not strictly like the Fermi level. This is sort of, I think, the surface potential of our system. So it's a little bit different than what we normally look at, but everything here you should be able to understand based on what we've looked at so far. So we have our semiconductor. We have a Fermi level here. This is the Fermi level of our electrons. And then we have this quasi-Fermi level for the holes, which sort of dips down like this. Now, I mentioned this a little bit before on our recitation section, but a quasi-Fermi level is just a Fermi level that exists in a non-equilibrium condition. So normally, a Fermi level is, you have our two Fermi levels for electrons and holes that are just equivalent to one another. Under illumination, remember we had that analogy of we have a whole bunch of electrons and we add a little bit, and then we have just a little bit of holes and we add a little bit. And that's going to seriously change the concentration of holes on one side of this band, right? So what happens is the bands come down. Just the holes though, because remember the electrons aren't really affected all that much because there's a much higher concentration of them. So that stays right about where it's supposed to be. Then it comes up here. I think this is from what's called the pinch-off effect, but the band sweeps back up and intersects our catalyst right here. Then we have a little bit of space here, which we'll get into in just a moment. And then we have a redox potential. In this case, we're looking at the oxygen evolution reaction. So this is a paper looking at sort of a solar fuels type motivation. And the big equation in solar fuels is 2H2O, oops, goes to H2, sorry, 2H2, 2H2 plus O2. So this is the full reaction, but really what it is, it's two half reactions added together. So there's the hydrogen evolution reaction and the oxygen evolution reaction. I'm going to write down the equations that are for the acidic version. So you can do this in acid or in base. And things are different depending on which one you do, but I'm going to pick the acid one just because it's a little bit easier. So the acid version, we have some protons. We have 2 protons plus 2 electrons going to 1 hydrogen. And remember, these protons are what you would get from an acidic medium. So these would actually be hydronium ions. And then we have on the other side, so this is called the hydrogen evolution reaction. Hydrogen evolution reaction. Then we have the oxygen evolution reaction, which is 2H2O going to, we'll do it this way. We'll write it as H2O going to 1/2 O2 plus 2H plus 2 electrons. So this is what's called the oxygen evolution reaction, OER. And you notice that these will cancel out on either side of the equation, and we'll end up back with our full equation. So you have to do both of these if you want to do water splitting. Typically, the oxygen evolution is tricky just because you need to put quite a bit of potential on it, and there's not like a ton of stuff that's stable in those conditions. Oxygen tends to like to react with a lot of things. But there's a few chemicals that are known to do that. Oxides are really good, like iridium oxide. And then one of the champions is nickel hydroxide, which turns into, under catalytic conditions, it turns into nickel oxyhydroxide. So this is like a nickel within a group like that. It's got like sort of a peroxy group, and you can maybe see that those peroxy groups are usually pretty weak, and it starts to look like that might actually be pretty good at getting some oxygen out there. All right. So that's why they're interested in this reaction. You want to get this reaction to go quickly because your rate, just like we were talking about with problem set 3, is your rate is going to, problem set 4. Your total chemical reaction rate is going to be limited by your slowest step. So you want both of these reaction rates to go as quickly as possible so that you can run the overall water splitting as quickly as possible. Really, the hydrogen reaction is the one we're typically more interested in. The oxygen's kind of waste, but you just usually vent it to the atmosphere. But you need to get that reaction to go as quickly as possible so you can get more hydrogen. Because typically the hydrogen evolution reactions tend to be pretty quick. So let's look at what's happening at this interface. So we have light that comes into our semiconductor. Then we have an electron hole pair that's generated. So we have the electron that jumps up here. We have our exciton pair. And then this hole, just like we've seen before, it creates a photocurrent. And it creates a photocurrent by moving to the catalyst level. Now, this difference between the catalyst level and the redox level, which is where the hole is going to go next, is called the overpotential, or eta. You want that to be actually as small as possible. So what that eta tells you, that is energy, that's potential that you need to put into your reaction in order to run, in order to actually run this reaction that's more than the thermodynamic limit. Let me explain. So water splitting, in theory, it takes 1.23 volts to do water splitting. In practice, it usually takes 1.7. And that difference, so that, like, let's just say that's 1.2 to make the math easier. The difference there, the overpotential, is then 1/2 volt. So in other words, what I'm saying here is that if you tried to use a practical system, like something that we use today in an electrolyzer, and you set it to 1.2 volts, you will get nothing. Even though you are at the thermodynamic limit, and in theory, you should be able to get water at that level, there is an overpotential in your system. Which is basically, it's accounting for things like kinetics. Like you need to give a little bit more driving force for these individual steps to happen. And because you have that, you actually have to boost the energy you put into it in order to run the reaction. So a small overpotential is good because that means you're not wasting energy. The overpotential is just waste. Yeah, come back to that. You also might notice, if you read the paper, that there are a whole bunch of equations for the current, which should look kind of familiar to you. So for example, here, this is the current from the semiconductor to the catalyst, and you should see a forward rate constant for the holes. We have the concentration of holes and the concentration of holes at equilibrium. And then we have the similar thing for the electrons. Then one of the things that they do is they do a simplification, and they say, well, we are assuming that the number of electrons currently is basically the same as the number of electrons at equilibrium. Remember, so we're making that approximation. And so that just falls out of the equation, and they end up saying, or we approximate that the current looks like this, which would be equal to Kp delta P. Right. So we are actually using some of the reaction, or some of the equations that we've been learning. All right. So then the second step, we have our hole that's in our catalyst. It then jumps over to our redox potential. Remember, it needs that little bit of boost to actually make that hop. And once it does, we have our H2O, which then makes a whole bunch of bubbles of O2. Fabulous. All right. So the main thing that they actually look in, they don't care so much about like this. This is somewhat well known. This is just background for you. The main point that they want to know is like, does the barrier height change based on the catalyst morphology? So they look at catalysts that are both like solid slabs, and I say slab, but you know, like just a tightly packed thin film versus porous catalysts. So I mentioned that iridium oxide and nickel oxyhydroxide are two examples of oxygen evolution catalysts. Well, iridium oxide is in the slab case, and nickel oxyhydroxide is in the porous case. And so what they point out is that if you look at these things, well, at the catalyst, you're just like normal, like you can imagine like a semiconductor interface. You're taking holes and you're putting them over here. So you actually are building up a little bit of what we call a double layer. We're not actually building up a depletion layer. That's something for semiconductors, but you're building up a double layer. And when you do that, you just like in a depletion layer, we build up an electric field, right? And if we build up an electric field, we build up a voltage. And so you might see in some of the diagrams that they have like the vacuum level. So like evac, and this is just like space. And in this case, the one over here, the slab, the potential changes, like the vacuum level changes. And that jump in the vacuum level is due to that potential, that voltage existing in the system. Now, notice that we don't actually change a whole lot about the semiconductor chemically, and like if you look at some of the later figures, the energy level, that surface potential, but the energy level for the catalyst doesn't change once it's illuminated, even though we are building up this little bit of voltage. And the reason it doesn't is because this right here is very thin. This region in here is much thicker, and there is no electric field in there. And since there's no electric field in there, it basically just acts like bulk iridium oxide. So there's not much of a difference there chemically. On the other hand, the nickel oxyhydroxide is porous, and it has a whole bunch of like little tiny particles in it. And when you do that, you are still building up that like little thin layer, but that little thin layer starts to impact almost the entire particle. And not only that, but before over here, these counter ions in solution are limited to be on the surface. They have to just like stick to the barrier, and that's where we get that voltage. They stick to the surface, but they can't actually compensate the charge. In a porous system, they can. So in a porous system, these ions can intercalate into our catalyst system. And even though there will be electric fields in between these two, you know, kind of like this, right? They're all kind of wrapped up, and everything is able to compensate itself. And so in that region, there's not a net electric field, which means there's not a net voltage drop. So over here, things can't move, they can't intercalate, which means we build up a voltage. Over here, what they point out is that the ions can intercalate, and thus we can compensate the voltage. And that's why we don't get a voltage at the interface. And if you looked at that EVAC versus space for the nickel oxyhydroxide case, it's flat because there is no voltage. There's no voltage, there's no change in the vacuum level. And they also bring up the fact that the barrier height, or rather the effective barrier height, changes for these porous systems. And the reason for that, just like I mentioned before, is because we have a whole bunch of that charge building up through much more of the system. So the work function of a material is how difficult it is to remove an electron from it. So this is what it looks like for a bulk system. And in our slab catalyst, remember, we have just this tiny little sliver right here of actual charging. And so most of the system is acting exactly like the bulk. So it's just as easy to pull an electron off of this material when it's being catalytic as when it is just sitting there. However, in our porous case, because we have this field going all the way through, kind of what you're doing is almost like fully oxidizing or fully reducing your surface. So it's almost like having, you know, iron 2+ in the solution, and then you just turn it all the way into iron 3+. Where over here, we're saying that there would just be a teeny, teeny, tiny amount of iron 3+, so it doesn't really affect the potential that much. In this case, we're getting almost all of it is iron 3. Or in this case, I think it's like nickel 3 and nickel 4. So when you do that, you are changing how difficult it is to hold on to something, right? So if you want to think about your chemical intuition, right? So this is like some metal. This is the metal with just a tiny amount of positive charge. And this is almost all of it is a metal with a positive charge. And think about, if you have a positive charge, it's going to hold on to the electrons more, right? And so since it's holding on to the electrons more, the effective work function is higher in these systems. And that causes all sorts of chemical effects. In particular, what it does is it affects your overpotential. That's one of the things that they show, is that you can actually show inside these systems that this overpotential can change in there based on the oxidation state of your catalyst. And so the main thing that they're looking at is like where the potential drops. Because then they're saying like, okay, you know, if we're looking at some of these catalysts and we're looking at them as just slabs, yeah, okay, maybe they are just bad catalysts, but if we made them porous, their behavior is going to change actually quite a bit. And so it could be that maybe, I don't know, like an iron film, let's just say, is a pretty bad oxygen evolution catalyst, which I think it is. But maybe if we turn it into a porous iron film, now we can change the electrochemistry of it quite a bit, because we can turn it from like iron metal to iron, say, 2+. And doing that will affect the overpotentials for the reaction. So before, where we were limited to say like, oh, okay, so this one's a good catalyst. But if we swap out the entire catalyst system, oh, this is a bad catalyst. And so we would have to, you know, completely swap out the system to just pick whatever was the good catalyst. What they're showing is that actually, if you start to mess with the morphology, so if you start to mess with what it looks like physically, you can also start to mess with how good of a catalyst it is. So that's sort of what we are going to get out of the Boettcher group, that we have these catalytic systems, which are very, very common in photoelectrochemistry. And we learned a little bit about quasi-Fermi levels. We learned a little bit about overpotentials, which are all very important in considering how these catalytic systems work. And then we learned a little bit from them, which is that if you change the surface morphology of these catalyst films, you can actually radically change the way that the system responds. And you can change how good of a catalyst it is. You can change its overpotential. All right, the second paper is I'm going to go over in a little bit less detail, partially because I understand it worse, because it's got a little bit more biology in it, which is really not my area of expertise. But it's a JAX paper from the Reisner group at Cambridge over in England. And it is completely different than what we've been learning about. It is still photoelectrochemistry, so I think it's a good thing to expose you to. But in this case, we're actually doing electrochemistry on a photoresponsive film that is biological. So we talked a little bit about plants and how plants do photosynthesis, and that is technically a photochemical reaction. So the question is, like, what if we tried to do electrochemistry with it? Turns out cool stuff happens. But first, I need to explain a little bit of electrochemistry to you, because they do something called a rotating ring disc electrode experiment. Now, in brief, a rotating disc electrode is an experiment where you take a disc. Literally, it almost looks like the end of this pen here. You stick it into a solution, and then you just spin it like crazy. And when you do that, you create a laminar flow of solution that goes up, and it is a constant laminar flow, which is actually really important. It's not turbulent, so you get like a really nice mass transport profile. So it goes all the way up, impacts the ring, and then it kind of just gets kicked out like that. And so you have a constant flow of stuff, and your reactants are immediately kicked out for a rotating disc electrode. What that means is you can only really run one reaction for a rotating disc electrode. And if you're interested in like what's going on over here, I mean, there's nothing you can do about it. You kicked it out of your system as sort of a payment for having really, really good mass transport. By the way, mass transport is just how it's just getting stuff to the electrode so you can actually do experiments. But they use a rotating ring disc electrode. So there's two electrodes here now. There's the same disc in the middle like we had before, but now we have a ring around the outside. And that ring allows us to examine the products. So you can imagine if we have a chemical system that goes from A to B to C, we have the A that comes in, reacts with our disc electrode, gets kicked out, but then we can catch it with the ring electrode and do chemistry there before kicking out C. So that's what rotating ring disc electrodes, it allows you to look at products of electrochemical reactions with really, really good mass transport. So you can get things that are relatively short-lived because they just move super fast. Think of it like ultra-fast spectroscopy, kind of, sort of. So remember, plants are photosynthetic, and photosystem 2 is the oxygen evolving complex. That so when a plant, we all talk about how trees make oxygen, and that's really, really important. Actually, it's mostly algae in the Pacific Ocean, but we have plants that can make a whole bunch of oxygen, and the way that it does that is it takes in water, splits it up, and makes oxygen out of it. Now, this is exactly what we're looking for like water splitting, right? I mean, it puts the protons somewhere else, but hey, it seems to work pretty well. Photosynthesis is like 4% efficient. That's not bad. A lot of photoelectrochemical systems are way less efficient than that. But because it's a biological system, they're very complicated, and it's difficult to tell sometimes what exactly is going on in there and what are the products that it's making. What's the mechanism? Is the plant using a different mechanism than we are? So what they want to do is figure out what is going on inside that photosystem too. They want to start a reaction and measure the products. So what they're going to do is they're going to shine light on the photosystem. They're going to vary the potential. So this is actually going to be hooked onto that disc electrode. And what they're going to do is by varying the potentials, they're going to be able to tell where the potentials inside of it are. Think of it like how we have VOC, right? So we have that VOC where that's where the hole current and the electron current are equal to one another, and that can help you figure out what your photovoltage is, and so what that splitting in your quasi-Fermi levels is. Similarly, you can use things like the dark saturation current to figure out, say, like what a built-in voltage might be, or some other like chemical potentials of these systems. So you can vary the voltage, look at what the currents are, and like look at where it starts to take off, and that'll tell you about the chemical potentials inside of that system. So it's a lot like IV curves. And one of the cool things I thought was they had a plot that showed the photosystem 2 with an oxygen-free system, and no matter what the voltage was, nothing. They got no current out of it whatsoever. I thought that was kind of cool. But as soon as they put air in there, and it wasn't even like pure oxygen, it was like 20% oxygen in the air, and it just kicks off. I think it was about at 0.4 volts, something like that. And it just starts going, and it's going because it's doing oxygen evolution. So the big takeaway from this paper is that hydrogen peroxide is one of the intermediates in photosystem 2's mechanism. So what they do is they actually are able to detect the hydrogen peroxide using their rotating ring disc electrode. So they have the water that comes in reacts with the photosystem 2, but because we're like really just moving this solution, as the photosystem 2 is making its products, they are just being ripped away from it. So where normally, say in the plant, everything's nice and calm, and it would make this peroxide, and it would go and do other stuff inside the plant, or maybe it would only live for a fraction of a microsecond before reacting with something else. Here, we're able to rip it out of the photosystem 2 and react it at the ring electrode. And the ring electrode, like the hydrogen peroxide reaction, is very well known, and you can sort of figure out, you can do like sweeps and things to figure out exactly what the identity of this chemical is. But that's what they did, is they figured out that, oh, we're seeing this other chemical that's coming out here, and that other chemical is the hydrogen peroxide, and that is what ends up going to the oxygen later on. So that's the big takeaway here, is that hydrogen peroxide is one of the intermediates in photosystem 2 water oxidation, and you can use photoelectrochemistry to figure that out. So hopefully you see now that photoelectrochemistry, we can use it to do catalysis, we can use it to study the chemistry of interfaces, we can use it to study these really important solar fuels reactions, we can do some fundamental semiconductor physics with it, and we can even do a little bit of biology. So that's sort of our quick little overview of the modern photoelectrochemical literature. And I'll see you next time.